So first of all, thank you very much for attending this workshop. I hope you guys will enjoy it as much as I will and learn as much as I will. So let's get started. So we're going to start with a recap of what we did last time. Ouch, that's a bit annoying. Let me fix this by running the presentation. Okay, let me first just try refreshing. And if that doesn't work, which it didn't, let me just run the presentation locally, and I'll fix it later on so you guys can see the entire presentation online later on as well. So last time we talked about these bottom three in the dependency graph for understanding from verification. So just a very quick recap, the Ethereum virtual machine is the execution environment for Ethereum transactions. There are 140 opcodes currently. That actually includes Constantinople, so in a few months there will be that many, but really there are only about 75 because log, swap, and dupe, as well as push, have multiple versions depending on how many bytes they take in as an argument. We also discussed the K language, which is used to define programming languages and virtual machines in a rigorous executable manner. To define a language in K, you define its syntax using the word syntax, its semantics in terms of rewrite rules using the keyword rule, as well as its configuration using the keyword configuration. Finally, we put those two things together and we got KEVM. KEVM is the Ethereum virtual machine defined in K. And just a very high-level overview, the configuration of KEVM comprises pretty much of these following categories. The call state, which includes all temporary stores that are specific to the execution of the current contract, such as the stack, the memory, the program counter, the message sender, the call data, the gas. You get the point. And obviously there can be, well, not obviously, but there can be multiple call states if you are calling another contract. Then there are also accounts, which comprise the accounts that are available for you in the network. Each account is composed of its address, its code, which is 0 for external accounts and non-zero for contracts. Its storage, which is also 0 for external accounts and non-zero for contracts potentially, as well as its balance, nonce, and I'm pretty sure I forgot one of them. The address, the storage, the balance, the nonce, and probably one more thing. And finally, we also have access to a bunch of block information, such as the difficulty, the Coinbase, the state root, the logs bloom, the mix hash, and on and on. So these are really the three big categories of the KEVM configuration. Today, we're going to discuss the remaining 4 topics. So we're going to start with symbolic execution in Z3, and finally get to K specifications and EDSL, and how to actually write K in the real world. So let's start with symbolic execution. Or I also wanted to say, and then once we put those 4 together, we'll be able to understand formal verification. And so said another way, the goal of this talk is to understand how K works behind the scenes, as well as to see how K is used in practice. So let's start with symbolic execution. A program can be executed concretely with specific arguments, or symbolically, where the arguments are treated as symbols, which is just a fancy way of saying variable. So during symbolic execution, we execute the program symbolically. And yeah, we execute the program, or I should say the control flow graph of the program would be a more specific way of saying that. And branching can occur as a result of this. Add conditional statements, such as if, while, and so on. But it can also occur elsewhere. For example, consider the EVM opcode add, or equivalently, the high-level solidity operator plus. If both of the arguments A, B are unconstrained EVM words, then the image or the output of the function can either be A plus B or A plus B minus 2 to the 256 in the case of overflow. So in that case, branching will occur during symbolic execution. And for example, for the opcode X, which does exponentiation, you can probably think that there will be an absolutely enormous amount of possibilities. And this is called path explosion. A path condition are the constraints that make the path feasible, i.e. reachable. Updating the path condition is equivalent to branching, if you think about it, because the only time you can branch is when there are several possibilities, and each of those possibilities will have an updated path condition, and vice versa. The only time you can update the path condition is if there was some kind of division necessary of the set of inputs that currently comprise the path condition. And the solution to the path condition will therefore be a test input for that path. So, K-framework uses symbolic execution to prove program correctness. But how does it actually prove it? So that's where Z3 comes in. So Z3 is a software built by Microsoft Research that, to my knowledge, from what I've seen so far, every single EVM formula verification tool uses for proving. So let's first take a step back and talk about the SAT problem in theoretical computer science. The SAT problem is the problem of satisfiability of Boolean formulas. For example, does there exist an interpretation, i.e. a truth assignment, for variables A, B, and C such that not A or B and C is true? So actually think about it, but let me think about it right now. Is the answer yes or no? The answer is yes, because you can make A false, or you can make B and C true. And the SAT problem is known to be MP complete, which was proved in the Cook-Levin theorem. If we want a solution to a SAT problem, we use a SAT solver, which therefore runs in hyperpolynomial time. A SAT solver takes as an input conjunctive normal form Boolean expression, which is just a Boolean expression that is a conjunction, i.e. an AND of a number of clauses, where each clause is either a literal, not literal, or a disjunction, i.e. an OR operator of other literals or not literals. So the SAT solver takes as an input a CNF Boolean expression, and it outputs either a solution or it proves that it's unsatisfiable, and does this just by brute forcing it. And the reason we use a conjunctive normal form, a conjunction of clauses that are each themselves disjunction, is because it better corresponds to most use cases. For example, in our case, path conditions. And also because there exists a polynomial time reduction from SAT to what's called 3-SAT, which was proved by a guy called Karp. And 3-SAT is essentially the SAT problem where each of the conjunctions has at most 3 literals, or not a literal. You guys know what I mean by not a literal, right? The logical not and then a literal. The fun fact here is that disjunctive normal form can actually be solved in polynomial time. So then that begs the question, why don't we use the DNF instead? And apart from the fact that it doesn't correspond to most of the use cases, it's that the main reason is that no algorithm actually exists to transform an arbitrary Boolean formula to disjunctive normal form. And in most of the stuff that we discussed in the last 2 slides, finding such an algorithm would actually imply P is equal to NP. So it's very likely that we'll never find it. Cool. So for formal verification, we need more expressiveness than just Boolean formulas. So we use SMT solvers. And SMT solver stands for satisfiability modulo theories. Here, theory has its mathematical meaning and axiomatic system. For example, integer arithmetic. And again, the solver will output either a solution to the problem, or after it brute forces them all, it will output unsat for unsatisfiable. So how do we prove properties over a set of integers? For example, let x be even. Prove that x squared is always divisible by 4. So we can feed the variable, in this case x, the constraint, in this case it's parity, and the equation, in this case x squared is not congruent to 0 mod 4, into an SMT solver. And if it outputs unsat, we actually, so if it outputs unsat, it means that that the negation of what we want to prove is unsatisfiable. And that's just another way of saying that the condition we want to prove is always satisfied. So in that case, we prove the property. Finally, Z3 is just an instantiation of an SMT solver. Now, by the way, off topic, if you guys want to know more about how SMT solvers actually work, there is a very good answer on Quora. I know Quora doesn't tend to be the go-to place for deep tech, but this answer is actually very good. It's about 2 A4 pages, and I can send it to you later on to get a high-level overview of how SMT solvers work. So a little intermezzo between the 2 parts. High-level overview. K executes your program symbolically, branching if necessary. At some point, Z3 will try to prove the post condition. If it can do so for all paths, the spec is proved. If at least one path has an irreducible term, it terminates and the spec is not proved. So essentially, formal verification is formal specification, which is done manually, plus a formal proof, which is automated. So in this section, we'll connect what we've discussed to how to actually use K. A K specification usually involves exactly one spec rule. Unlike semantic rules, which specify rewrite rules, it specifies what we want to prove. in particular, a precondition, which comprises of the initial contents of the configuration cells. And that depends on the language you're working in this case, the EVM, or more specifically, KEVM. And also the postconditions, which are the desired contents of the configuration cells after the execution. And the precondition and postcondition are separated by actually the rewrite sign in K, which I understand it can be confusing because we use the same symbol for both defining programming languages and virtual machines, and also for writing specifications, and those two are very different. In some way you could think of them as opposites, because the semantic rules are what we assume and the spec rules are what we want to prove. But that's just the notation that we got to deal with. The pre and post conditions can also be constrained using the keywords requires for preconditions and ensures for post conditions. And together, the pre and post conditions, when used for program correctness, express the intended behavior of the contract. So this has all been pretty theoretical. So let's dive into an example. Let's say we have a super simple language, IMP, for a super simple imperative language that has a configuration comprising of two cells. The K cell holds the program that is executing, and state is a map. It's initialized with an empty map. Dot in K means empty, and then you write what type it is. So this is an empty map. And then in the future, it can potentially hold values for our variables. So in this super simple imperative language, by the way, we haven't defined the language. We just defined its configuration. But let's assume you can imagine the rest. Then a possible case specification would be the program y is equal to x, and after execution, it will disappear because it's been executed. We take the lines of code as they're being executed from the K cell. And most importantly, the state, it will be initialized with the variable x, which has some value we call x value. And afterwards, it will end with y having that same value. And a really cool thing about K is that we can also put in this little symbol right here, which actually, wait, let me try to. This little symbol right here, I can't, okay, which in K means an anonymous variable. Anything will match this variable. And it's of type map. So essentially what this left-hand side of the spec rule says is that the state will be initialized with x having some value. By the way, we put no constraints on it. So these are fully unbounded integers, actually. And then there can be anything else in the map. So that's the key point here, is that we will be doing the full notification symbolically over all possible initial states of the program. So that's really important, but also really, really cool. And the same exact thing for the right-hand side. We say that y must get this x value, but we don't care about what will happen to anything else apart from y. So, probably nothing else will happen, but Basically, this allows us to decrease our troubles, to prove only what is important and not care about the rest. So we'll see that later on in the presentation for specifications for EVM functions. So we can also include constraints on our variables. So consider this other very simple int program. Y is x mod 2. And what do we want to prove happens to this after this program is executed? So the precondition will be that that the program comprises of this line of code, and that x has some value, x value. And the postcondition will be that this line of code has been executed. So we have, remember, dot is empty in K. And let's see if I did it right. Yes. And y will have the value 0. And the reason for that is we will assume that x value is even. So the point that I'm trying to make here is that we would also have to have another specification for odd x's, because every single specification tests one case of a function. So I just wanted to illustrate that you can also constrain your preconditions. Here I constrained my initial value for x, but then it's often the case that you need to write multiple specifications in order to cover all the cases. Fun fact, right now there is no automated way to prove that you actually covered all of the cases. So this is, again, a deeply manual thing. And if you make a mistake in that, if you don't cover all of the possible cases in your various specifications, you will not prove program correctness. Very important. Okay, let's go a little bit deeper. So what are the different possibilities in one cell? The most popular are either static spec rules. By the way, I made this word up, static spec rule, but I think after I explain it, you will see why it makes a lot of sense. So static spec rules are ones that don't contain the rewrite symbol. In other words, the precondition has to equal the postcondition. So let's take a look. So examples of that are essentially you can have three possibilities here. You can have a value type. So an example of that is the call data. So the call data for a function, it should remain constant throughout the entire execution of the contract. Another example would be the code for an account that shouldn't change. In fact, that can't change. The code of a contract can never change in Ethereum. Here I obviously omitted the actual code, but this would be 0x 64 FC blah blah blah. Another example would be specifying a call value of 0 when, for example, we want to test the success case, the positive case for a payable function. A payable function is one that cannot accept a call value. Another example would be where we want to specify a mode for the execution, which is essentially the EVM version that we want to use. So in this case, we're using the latest version. You can also put in anonymous variables. What that means is that we actually don't care what is in that cell. We just care that it's constant. So for example, The gas price, that actually doesn't have an effect once the execution has started. And then some network information, such as the hash of the last 256 blocks, balance of an account, say, and so on. Finally, we can also name the variables. So we keep them as symbolic, but we give them names. So an example of that would be naming the call value. So this would be in a failure case, in the negative case for a payable function. The reason we name variables is oftentimes precisely to put constraints on them. So we could call this call value, and then we could say requires call value be greater than 0. And what that would do is that would test the negative failure case for a payable function. Then we would say that we want execution to end with revert, for example. So this would be the precondition, and actually also the postcondition for this particular cell. Another example would be the message sender, because we want to constrain it. We always want to constrain this, and the reason is that if we don't, it will end up being an unbounded integer. But we want it to be between 0 and 2 to the 256, 2 to the 160 as an integer. The most popular or the most interesting spec rules are dynamic ones. So, for example, in the K cell, oh, by the way, I should mention, remember how in IMP we put the entire program in the K cell? In KEVM, it works differently. The program will go into a cell called program, and then the K cell holds kind of what you might call the internal opcodes of the EVM, of KEVM. So in this case, we want execution to begin with the internal opcode execute, and we want it to end with a halt. The program doesn't loop forever. And yeah, so that's one example. So this example is where we have a value type as a precondition and another value type as a postcondition. We could also have an anonymous variable as a precondition and a value type as a postcondition. An example of that would be output. Usually, this is the way it's written. This in particular is the output spec for the transfer function in ERC20, the success case. So we don't care what there was before, but we always want to return a value of 1, because that's what some ERC20 functions return in the success case. But we could also have a value type as a precondition and an anonymous variable as a postcondition. This is very, very frequent. Examples include the program counter. We set it to begin at 0 so that we actually execute the program from the beginning, not from the middle. But we don't really care what it ends up being. That's not part of our specification. We care more about the output, the storage modifications, etc. Another example would be the word stack, memory, and many others where like these transient non-permanent stores, such as the stack, the memory, and so on, that will disappear once the call is ended. Another one could be gas, because again, unless you're doing some kind of fancy gas analysis, we don't care what the gas ends up being afterwards. I should note that if it ever goes to 0 or below 0, we will get an exception, out of gas exception. So that is already handled as part of the semantics of KEVM. Cool. So now let's put everything that has been talked about together, and you can have this beautiful contents. This is the contents of a cell called storage for an account, for specifically a contract. And here we're going to say the hashed location, the storage slot for this particular variable should, and here's the precondition, right? So here's a map. This is a map, so it maps the storage slot to some value, and here's the value. And inside the value, we see a spec rule, right? A pre and post condition separation. So it will begin with some value that we name as balance from, and it will end up with the same value minus the variable value. And you can see that the second line does pretty much the same thing, except with different symbols. So can you guys think of what function this corresponds to? So I should say that value is passed into the function in the call data, and so is toID.
Probably transfer, right?
Yes, thank you. This will be the transfer function, exactly. And one more really cool thing is I said that we name variables to put constraints on them. That's true. But as we can see, we also name variables to use them somewhere else in our specification. So I should have said that. That's another possible use case of naming the variables, not keeping them anonymous. Cool. And as before, we don't care at all about the rest of the storage. In other words, the rest of the storage can be whatever it wants initially and cannot change. So that brings modularity to the transfer function. The transfer function can only change these two storage slots, and in this very specific way. Cool. So also I should mention that as I said, we have one spec rule for one case of a function. For very simple functions like ERC20 functions, we usually have about, from experience, about 2 success cases and about 3 failure cases. But if we were specifying a very complex function, such as one in the among the core functions, the Dutch exchange, it's very likely that there would be maybe 11 failure cases. And the reason for that is that the number of failure cases grows with the number of asserts or requires in your code, or equivalently, the number of conditional reverts in the bytecode. Cool. So now that we've seen fragments of it, here's actually the full specification of transfer success 1. So first of all, what is transfer success 1? So transfer has 2 success cases. One is where you're transferring to yourself, and the other one is where you're transferring to a different address. So in Solidity or on the EVM level, those are not distinguished. But by the way the K matching algorithm works, we have to distinguish them. And from what I know, all formal verification tools have to distinguish these 2 cases. It's a common pattern among formal verification tools. So here it goes. We have the full EVM specification, configuration, as we saw it last time 1 month ago. And but this time we actually have the preconditions and postconditions specified in every single cell. By the way, I have, again, omitted the code from here, and in the network section. And the reason for that is that that would take up a lot of space. So this is it pretty much. This is our case specification, the manual part that we have to write. And once we get that, K will do its proving. Pretty much, I was gonna say fully, but pretty much is a more accurate word, automatically. And yeah, and we can also see fragments of the examples that we saw before. So everything that I gave in the previous 3 slides as examples, it's all over here. So I wasn't confusing you guys. So for example, right over here, we have the storage specification, as Adam mentioned. Cool. Oh yeah, and we also have a bunch of require statements that, as we discussed, constrain our preconditions. So for example, we want all of the addresses that we use in the specification to be valid EVM addresses. Oops, whoa. Additionally, we want the call depth not to exceed 1023, because the call depth in the EVM is at most 1023. So if we set the call depth to be 1024, it would throw an exception immediately, even before it executed the very first opcode. And we also have to set bounds for the values that we are either passing in as call data or naming as part of the initial contents of storage. Because both the call data that we're passing in and the initial contents of storage, they're EVM words. And so we have to tell K that. And what distinguishes this case from the other cases for transfer is that we are not transferring to ourselves, that the amount we are transferring, it doesn't exceed how much we own, and additionally that the value that will get transferred to the different person will not overflow. So these 3 assumptions are very important because they distinguish this particular spec from the 4 other ones for the same function. Okay, so that was quite a lot of content already, but now we're going to go into the practical stuff. So essentially, I've cheated a little. Not everything that you saw above were actual EVM semantic rules. To make life easier for ourselves, we usually write specifications in EDSL. So EDSL stands for Ethereum Domain Specific Language. And it is used to make it easier to write common patterns, which are derived either from Solidity or from the application binary interface standard. So in particular, there's actually just 3. And those are, for some reason it didn't put it on a new line, but the first one is this one, ABI call data. The second one is this one, ABI event log. And the third one is hash location. So as you can probably see, if we didn't have access to this beautiful function, we would actually have to specify the call data in the in the specification rule as a bunch of bytes. But that is very unreadable and not very easy to work with. So instead, we specify the call data as a function, and it will ABI encode the parameters. So in other words, it will take the regular ABI process. It will take the hash of the signature. It will take the 4 bytes of that, and finally, it will yes, it will make 2ID. It will pad it to 32 bytes, and similarly for value, and it will concatenate it together and put it in our call data cell. Cool. Another one is events. We use that here as well because part of the strong requirement on ERC20 is that the contract fires off an event when transfer has been executed successfully. So we are using that right over here, so we don't have to go to low-level details. And, and finally, we are also using that right over here. So this is actually going to be equal to yes, it's going to be equal to the hash of the argument, comma, the storage slot. So the hash of this, comma 0, is actually going to be the storage location for a mapping value of 2ID. But since we don't want to deal with that, we just write hash location. So EDSL, it makes it easier to write common patterns, but not only that, it also allows us to use EDSL templates. So here, I didn't think I could do a better job than the official K documentation. EVM specifications are written over the full KEVM configuration. However, a large part of the configuration can be shared across specifications. EDSL allows capturing such common portions in the form of a template specification that can then be instantiated for each specification. So to use K, we, number 1, need a spec template, which will be a K file. And here's an example of the spec template for GNO ERC20, for the GNO token. The spec template is composed of 3 things. Rules that are the same across all the different specifications, i.e. all the different functions and all their cases. It's composed of function-specific parameters. And it's also composed of program-specific parameters. I think that's this one because we always assume gas is 100,000 for GNO ERC20. Even better examples would be, let's look at some good examples, code. So for the entire program, we want the code to be the same. So that's a program-specific parameter. And let's look at the bottom. Actually, let's go through it in order. So K, we actually want this to always be the same. So technically, it's a program-specific variable because we just write execute leads to halt. Output, this is function-specific. Status code, this is even case-specific. So it's technically function specific. Code, as we said, is program specific. So function general. Call data and call value are both function specific. And yeah, I mean, you kind of get the idea. So we need a spec template. We also need the function and program parameter file. So the reason this is so interesting is this is actually the file that we are working with 99% of the time while doing firmware verification. So this file contains all of the functions and all of the cases that we want to verify. So for shortness, I just put 2 or 3 functions here. 3. I have total supply. I have balance of, and finally I have our favorite, transfer. And it works as a regular ini file, so I don't think there's much to say about it. This root will get inherited from every single class. This defines what is generically true across all total supply cases. This defines a total supply case. This defines a total supply failure case. Same for balance and balance of. And finally, for transfer, we also have subclasses for success, because there's more than one of them. And finally, we also have subclasses for failure. And let's look at just one of them to see how it actually works. So here, so transfer, what is true across all transfer cases? Well, definitely the call data, because the call data actually specifies that we're calling transfer. What is true across all transfer success cases? Well, we don't revert, and it returns 1, and it should fire off an event. And since it's a non-payable function, the call value has to be 0. And finally, we have when we're transferring to somebody else, and when we're transferring to ourselves. What's true for all failure cases? Well, they don't produce a log. One of them reverts. When do we get revert? Let's have a look. When we are trying to give the other person more than we have. When do we get another revert? When we are trying to give ourselves more than we have, right? And when do we get an invalid instruction? When the call value exceeds 0. So when we are transferring ether to a non-payable transfer function. And finally, we have the program generic variables or parameters. Here we're using Solidity as our compiler. The only reason this is important is to make our life easier for finding the storage locations for storage variables. That's the only time we use compiler, as far as I remember. We also need to specify the storage positions of variables that we want to use, such as balances, which is a mapping from address to uint. And finally, the code and the gas will always be the same. I truncated this for simplicity, but we already talked about both of them. So, everyone awake? How do we actually use K? So you start by generating all of the spec files from the ini file together with the spec template. Or let's see what I wrote. I wrote spec template plus template parameter ini file generates K specification files. And once you have generated all of the K specification files, you run kprove. You run it in the following way. You say kprove, then you say the spec that you want to run. Actually, this should have -spec.k. Typo. Then you say where your language definition is located. And finally, you say which, or actually, I think this is where K is located. And then you say where KEVM is located. So you pass in the KEVM and K tools. K currently has a Java backend for symbolic execution. So that's the one I'm using. Okay. So if a spec cannot be proved, we get some information. In particular, we get a bunch of steps. Now, each step is a K rewrite rule. Usually about 15 steps correspond to one EVM opcode execution for simple opcodes. The reason for this is that, as we saw in the previous presentation, there are a bunch of internal opcodes that a EVM uses. So, for example, at each opcode, it will use the following internal opcodes: next, to actually load the next opcode; exceptional, to check whether it's an exceptional opcode; invalid, to check whether it's an invalid opcode; stack needed, to check whether it requires more stack than we currently have. It will check whether it's a static opcode, and if we are doing a static call, then it needs to revert, right? You can't do non-static opcodes during a static call. Then it needs to subtract the gas, which for complex opcodes can require a few dozen internal opcodes, because you might have to subtract gas for the memory being used, the storage being used, etc., and for the actual opcode as well. And finally, it executes the opcode. And then also it has to increment the program counter. So there's a bunch of things that go to just one single opcode execution, EVM opcode execution. Cool. So what was I going to say? How do you actually debug K outputs? So you run kprove with options like log cells, debug z3, etc. And it very often times generates a file of several hundreds of thousands of lines, even millions of lines, in a couple of minutes or a couple of dozen minutes. Yeah, that could improve. And then you have to find the problem. So the problem is, in my limited current experience, usually an irreduced term is the cause of a failed spec. So then you need to figure out what happened. Either your spec is not correct, in which case you have to fix the spec. Your spec is correct and K just needs a little human help. That's why I say it's not 100% automated. There are times when K struggles, and then you help it by writing a lemma. Or, in a rare case, but the most important case, your code is not correct. You have just discovered a security vulnerability. And that's the whole point for why we do formal verification. So to make running proofs in bulk and debugging easier, I've written a script that does that. And Yeah, it's pretty simple, and we'll see it in the demo, which is right now. So I'm going to show you a demo. Okay, so we are going to prove, i.e. formally verify, our favorite function, which throughout this talk has been transfer, in particular, the first success case. So, oops, here. So let's do that. So let's start by cding into the GNO directory. Finally, let's make the specification files from the spec template and the template parameter file. By the way, the contents of these two files are exactly as you have seen in the presentation. So there's nothing tricky going on here. Bam, so if everything went correct, we got a new folder called specs. And in that, we got a new folder called GNO. And here we have a list of our functions. And for each function, a list of the cases. And for each case, an actual K specification rule. So quite ironically, I clicked on the one that would be verifying. So that's pretty cool. Now let's actually run it. So to do that, I'm going to go back. And I'm going to use my script. And I'm going to say I want to run files from the directory GNO. And I'm going to say that I want it to output it in a directory called GNO1 because I can make a mistake. And in that case, we want to have 2 and 3 available. And finally, if I leave this open now, it will start verifying every single spec file, but we said we just want to do transfer success, the first case. And let's see if it works. So we don't have any options because I know it's going to work. So that's why this part is blank. Let's see who's actually remained. Nice. Appreciate it. So this usually takes about 2 minutes. So it shouldn't be very long anymore.
Okay, can I have a question in the meantime?
1 sec. If we did log, it would actually take about 40 minutes, and that's when you would get the millions lines of code. But when we don't log anything, it usually takes a significantly smaller portion of time. In other words, debugging is extremely costly, but writing good specification and good code is very cheap. Yeah, Adam, hit me.
Okay, you mentioned something that you have called path explosion. All right, so there are cases where you can have almost infinite amount of paths, right?
Yes.
So what are the strategies to deal with these cases?
So I am a super fortunate person in that none of the contracts I verified use the X opcode, or in particular, I never actually had a path explosion. So I don't know. I never encountered this yet, luckily for myself. I guess that K has some internal heuristics for handling this very effectively.
Okay. Mm.
So the verification is finished. So let's see if it has outputted an error log, and we do that by going to output and first checking out the log. Okay, so we verified it. Now what's the actual output? Nice. So we just verified that the precondition will always lead to the postcondition regardless of the value of any one of our symbolic variables, including storage. So that's pretty cool. And that's also the end of the demo. So do you guys have any more questions?
Great. I have one more. In your opinion, what differentiates a complete formal specification from implementation of the code you are trying to verify? Like, what's the difference? Because if you have a complete formation, you can almost use it instead of the code, right? Because
what?
you can use the specification in the place of the code, right? Instead of the code, almost, right? Like from a logical standpoint, because like that all of the rules.
Not necessarily. So I think I think that the K guys are working on this. At least they've hinted at it, being able to generate bytecode from K specifications, which would be, in my opinion, pretty revolutionary when it comes to both software development and theoretical computer science. But most in practice, it's not always very easy to equate the two. Consider a sorting algorithm.
Okay.
So specification will just say that it began unsorted and it ended up sorted, but there are numerous ways of how to implement that process, right?
But to check if you have actually, like, not only if all of the elements are sorted, right, but if the elements are identical to the elements you have started with, right, to like really check everything, right, you basically have to re-implement the program in the spec.
Not really, because it's much easier to check a sorting, to check whether a list is sorted than to sort it. Or I wouldn't say
no, you can check a list is sorted, but you also have to check the elements are identical with the original list, right?
Fair enough.
And
I'm not sure that those two things are identical to actually sorting it.
I think so. Like at least like, my mental math is or intuitively I think it's the same task.
Interesting.
Yeah.
Nick, are you still on the call? What do you think?
Yeah, I'm still on the call. My intuition is not necessarily, but at the same time, like to verify it, it has to use some search algorithm, right?
Yeah.
The solver is using some search algorithm.
I would have to think about this. It's a good food for thought.
Yeah, I like my intuition is that what differentiates like formal specification from the like the code that it's trying to verify, right, is that formal specification actually checks more stuff than the code, right?
Right.
In code you have like implicit assumptions, right?
Yes.
About the outputs or about the relationships between inputs and outputs, but in formal verification you actually like encode these implicit assumptions explicitly, right?
Exactly.
So you actually do more computation or more checking than the code, right? So formal specification is almost like a like it should be like the implementation, but more on top of it, right? That's my intuition, at least.
Yeah, I think that this is also my intuition. I feel also it kind of like the framework kind of forces you to think about all possible cases. Whereas if you just write let's say regular code, it doesn't like there. You it just has to work with like the couple of input parameters that you have thought about, and all the other cases. Well, who knows? Maybe it works, maybe it doesn't. But yeah, I also don't have a better explanation.
Okay.
But I was also wondering. So Dom, you mentioned basically. Well, you have to write the specification, right? And obviously, the specification also can have a bug. So, do we now need a formal verification of the formal verification spec? Yeah,
it's a really good question.
It's so fun.
The answer
or do you need to audit it at least?
But I think that there would be it would be useful if we had an algorithm that would check whether your different cases cover all the possible cases.
I think my answer to it is that if you don't care about efficiency, right, then you can, like, preventing bugs is much easier, right? So in the production code, you care about efficiency. So you have to rely on implicit assumptions. But in formal verification, because you don't care about efficiency, because the formal specification is not what actually runs, like in production, you have to you can encode much more things explicitly, and that makes it actually easier to catch bugs or to avoid bugs. So I think it's easier if you don't care about efficiency, like computational efficiency. You can write bug-proof code more easily, I think.
I totally.
I like that answer.
The main difference comes down to the type of execution, right? In regular real-world execution, we do concrete. With formal verification, we do it symbolically.
Well, like normal program, right? It's also a symbolical engine, right?
Right. But during execution, all the variables have specific values, at least in the EVM.
Yeah, in execution, yes, but if we are comparing the program and the specification, right? These are both symbolic systems, right? So
I see. Yeah, that's a really good way to look at it.
Yeah. Okay.
Cool. Any other comments or questions?
Do we need to audit the specification?
Yeah, I think so.
I think we do. I think
but it should be easier to audit than the code.
Got it. Yeah. Mm-hmm.
Yeah, I think that's the point.
Okay, makes sense.
Yeah.
Okay.
Cool, guys. Thanks for joining, and have a great weekend.
Thank you. You too.
You too. Thanks for the presentation. Yeah, I learned stuff.
Thanks, Dominic. See you later.